Okay, this is the second video lecture for Math 140, Trigonometry. And the topic today is inverse trigonometric functions. So if you remember from our last class, in our last video lecture, we talked about inverse functions. We talked about what a function is. We talked about what a one-to-one function is. We talked about the horizontal line test. And then we talked about inverse functions. You can only have an inverse function to a function if that function is one-to-one. And if it's one-to-one, what that means is that for every output, there's only one input, okay? And then we talked about how do you actually find an inverse function from a function. We went through a procedure to do that. Today, we're going to apply what we learned about inverse functions specifically to inverse trigonometric functions. If you guys remember, there are 6 basic trig functions: sine, cosine, tangent, cotangent, secant, and cosecant. So we're going to discuss the inverse trig functions as correspond to those 6 trig functions. Actually, we're only going to really do sine, cosine, and tangent today. We're not going to do the other 3. But those are the most important ones, and we will talk about these inverse trig functions. So that's the topic for today. The topic for today is inverse trig functions. Okay, this marker's a little bit dry, so I'll use another one. Okay, inverse trig functions. Let's start with the function y equals sine of x. Okay, this is our regular sine of x function, and what I'm going to do is create a graph of this. Okay, so we'll create a graph of sine of x. Start like that, go like this. Okay, sine of x, what it does is it comes down, it goes through 0, it goes back up, it comes down again, and so on. It oscillates like that. Okay, and it comes back up like that. And it comes back like this. And we can ask ourselves, is sine of x, it is a function, is it a one-to-one function? Okay? Well, the way we can tell is we can draw any horizontal line. So let's just draw a horizontal line like this. Okay. And it's a one-to-one function if that horizontal line only hits sine of x at one place. Now, looking at this, we can see that sine of x terribly fails the horizontal line test because not only it intersects not only 2 times, it intersects an infinite number of times. For each peak of sine of x, it'll intersect twice. So y equals sine of x terribly fails the horizontal line test. Therefore, it's not a one-to-one function. And it may seem like this is completely pointless because if we don't have a one-to-one function, we can't find an inverse function to that. However, there's a clever trick we can use. And the trick we use is we can restrict the domain of, so sine of x is not one-to-one. Sine of x doesn't have an inverse. But what we can do is we can restrict the domain of sine of x. So we're going to restrict the domain. Restrict domain. Normally, sine of x has a domain of x from minus infinity to plus infinity. But we're going to restrict the domain of sine of x such that x belongs to minus pi over 2 to pi over 2. We're going to severely restrict the domain of sine of x. So basically, what I'm going to do is draw this in red. So we're going to restrict the domain to just this point to this point. And recall that sine of x peaks at pi over 2, and it has its trough at minus pi over 2, and multiples, and so on. Okay. What we're going to do is restrict the domain of sine of x to just this segment along here. Just that segment. That's our new restricted domain of sine of x. Okay. Now, if we restrict the domain and then apply the horizontal line test to just this red segment does indeed pass the horizontal line test. So, and we're going to get rid of everything else. We're basically going to get rid of all the rest of sine of x. Just get rid of it. And just keep this one small section of sine of x. This small section of sine of x is, in fact, a one-to-one function, and so therefore this has an inverse. So that's kind of the clever trick we're using to find an inverse to sine of x. We're restricting the domain. Now, what does the inverse sine of x look like? What does its graph look like? Well, let's regraph sine of x. Let's zoom in a little bit. Let's be a little bit more careful about this. So we're going to draw sine of x. We have sine of x here. Okay, we'll draw our x and y axes. Okay, and let's be careful about this. This is sine of x. It's our new restricted domain will go like this. Will peek out like that. Okay, this occurs at pi over 2. This occurs at minus pi over 2. Okay, and the peak of sine of x occurs at 1, and the trough occurs at minus 1. Okay. What does the inverse trig function, this is sine of x, no doubt. What does the inverse trig function, inverse sine of x, look like? Well, what we can do is we can create a graph of it. And to do that, I'm going to mark this point. This is pi over 2. Pi over 2 is about, what is it, 1.6 or so. So this will be about pi over 2 down here, minus pi over 2. And I'm going to mark the point 1 right here, and minus 1. Okay, and the way this works is we're going to create points. So this is what inverse sine of x looks like. Okay, and what it does is it comes down like this. Then it switches over like that. This is now, I didn't draw that quite right, but this is now inverse sine of x. Inverse sine of x. If you guys remember, to find the graph of an inverse function, you basically reflect the actual function sine of x. You reflect it about the line y equals x. This is the line y equals x. So this is inverse sine of x is the reflection of sine of x about the line y equals x. This is the inverse sine of x. Okay, and if you've noticed, let's talk about the domain. Let's talk about inverse sine of x. So y equals inverse sine of x. Okay, what is the domain of inverse sine of x? What happens is we basically flip the domain and range for sine of x. So the domain of inverse sine of x runs from minus 1 to 1, and the range of inverse sine of x goes from minus pi over 2 to pi over 2. Okay. All right. That's the domain and range. So basically, this is the flip, the reverse or the flip of the domain and range of sine of x. And basically, when you graph the inverse of a function, you basically flip the x and y axes. So this is what we get for sine of x, for inverse sine of x. I'm going to go over to my computer now, my laptop, and show you guys in Desmos what we can do here. We can graph this in Desmos. So just hold on a bit as I type these in. This is now Desmos. We can have y equals sine of x, and that's what we get. And then on top of that, I can graph y equals arcsine. Arcsine is another name for inverse sine of x. And that's what we get. And so we see that the red is sine of x. To find the inverse of sine of x, we restrict the domain of sine of x to just this part from minus pi over 2 to pi over 2. And then inverse sine of x is the reflection of sine of x about the y equals x axis. And so this is inverse sine of x. Okay? And that's pretty cool. So we found our inverse function. Okay, back at the whiteboard. I want to talk about cosine of x. You might be curious about what's the inverse of cosine of x. So let's talk about that. Okay. Inverse cosine. So let's do y equals cosine of x. Okay. Let's graph cosine of x. It's going to look like this. And cosine of x, if you remember, goes like this. Like that, okay? And again, if we draw a horizontal line, the horizontal line will intersect cosine of x. If we draw some horizontal line like this, for instance, this horizontal line intersects cosine of x at many different places. Therefore, cosine of x is definitely not a one-to-one function, which you would think would mean we can't find an inverse. But what we're going to do again is do this clever trick of restricting the domain. Restrict the domain, this board bounces a lot over here. Restrict the domain of cosine of x, okay? And maybe you can see the domain we're going to restrict it to. We're actually going to restrict it, the domain, from here to here. Okay, what are these 2 points? These 2 points are, this point is pi over 2. This point is pi. This point is 0. So we're going to restrict the domain of cosine of x. Severely restrict it to 0 to pi. Okay? And if we do that, well, I can draw on this red curve here. That's my segment of cosine of x we're keeping. And basically I get rid of everything else, okay? Everything else outside of that. And I'm left with just this small segment of cosine of x. Now if you apply the horizontal line test to this small segment, this in fact is a one-to-one function. And so we have a function we can find an inverse for, okay? And let's see if we can graph what the inverse looks like a little more carefully. Okay, so I'm going to erase this and draw cosine of x a little more carefully and its inverse. Okay, so here we go. We've got our line here. We got cosine looking like this. Okay, and here's our cosine of x. Starting here, it's going to go down like this. It's going to go down to here. This is our restricted domain of cosine of x. Okay, this point is 1. This point is minus 1. Okay, this point is pi over 2. This point is pi. And this point is 0. Okay, I'm going to make a couple other marks here. Pi over 2 on this axis is about, well, I need to go a little bit higher, don't I? It's going to have to shoot up here. Pi is going to be somewhere like up here. I should have left a little more room, but you guys will get the idea. This is pi, and this is approximately pi over 2. Okay, and that's 0. Then I'm going to mark the point 1 and minus 1. This is 1, minus 1 and 1 along the x-axis. Okay. And then what I can do is I can put 2 points here. So we have a point right here, and we have a point right here. Okay. And cosine, the inverse cosine of x, will look like this. Oops, I got the point wrong. The point is right here. Excuse me. That was a momentary blip there. That's what we get. This function right here is cosine is inverse y equals inverse cosine of x. Okay? And you can see that basically we flip the points. Like this point right here is 1 comma, is 0 comma 1. Okay? Well, that point flipped, and we have to this point flipped to this point. This point right here is minus 1 pi. That's this point. So this point went to here, and basically what we've done is we've reflected cosine of x, this restricted segment of cosine x about a line y equals x to get our inverse cosine of x. This is what the inverse cosine of x looks like. I apologize for the little ripples in the graph there. Let's again go over to my laptop and let's look at this in Desmos so we can get a better graph of what's going on. Okay, so I'm going to erase all of this. We're going to do cosine of x. Cosine of x, that's cosine of x. Okay, and then we're going to do y equals arc cosine of x, and that's what we get. So we restrict the domain of cosine x from 0 to pi, and then we reflected about the line. Let me put a line y equals x here. Do you see how, in a weird way, this restricted segment of cosine x is that inverse cosine of x is the reflection of this restricted segment about y equals x. So this is our inverse cosine of x, the graph of it. You guys take a look at that. Okay, continuing to record, we're going to do one more function, which is tangent. Okay, we're going to do tangent together. Okay, let's do tangent. Then I'll do a couple quick fun example problems that will be easy for you guys. The good news for you guys is the problems I give you that relate to inverse trig functions are really easy and fun. So it doesn't get, it's not super crazy hard problems. Let's do tangent of x. Let's graph. So what if we have the function y equals tangent of x? Let's graph tangent of x. And so here we go. And basically we have, this is our y-axis. And if you remember, a tangent has vertical asymptotes at minus pi over 2 and pi over 2. And a tangent goes like this. And then it repeats. There's another vertical asymptote here. And it goes like this. And it goes like, this is pi. It goes like this. And so on. That's tangent of x. Okay? Let's take a look at that. I might have blocked your view there. Again, we can apply the horizontal line test here. And we have a problem because the horizontal line intersects tangent of x at many different places, in fact, an infinite number of places. Therefore, y equals tangent of x is not 1-to-1. We can't find an inverse. The clever way around this is we again restrict the domain. So we restrict the domain, See if you can guess what we restrict the domain to. We restrict the domain to x belongs to minus pi over 2 to pi over 2. That's our restricted domain, okay? So basically, we're going to get rid of all this stuff. Get rid of all this stuff, okay? And we're going to restrict the domain to just this. It's in green. Let me make this a better color. Let's do blue. Let's do blue. Blue and green, like some kind of aqua ocean color, and that's what we get. This is what we restrict the domain of tangent of x to these two values. And if we do this, now we have a 1-to-1 function which passes the horizontal line test. So let me draw for you guys. Let's do another graph where we draw the inverse tangent of x on here with our restricted domain. So here we go. Inverse tangent of x looks like this. Here we go right here. We have our vertical asymptotes like this. Okay, and tangent of x will look like this. Like that, okay. And then we can basically draw inverse tangent of x. So let me draw that in red. These points are pi over 2 right here. These are pi over 2. Pi over 2 and minus pi over 2. I'm going to place these same points up here. This is pi over 2 and minus pi over 2. These now become the horizontal asymptotes of the inverse tangent of x. Like that, okay? And if we graph the inverse tangent of x, it's going to look like this. Something like that. It shouldn't actually cross there. That's my bad. Slightly off there. It should really look like that. Okay. This is the inverse tangent of x. Okay. And this is tan x right here. Inverse tangent of x, tan x. Okay. And basically things were kind of flipped. While tangent of x had vertical asymptotes at minus pi over 2 and pi over 2, inverse tangent of x has horizontal asymptotes at minus pi over 2 and pi over 2. Let's talk about the domain and range of inverse tangent of x. What is the domain? See if you guys can identify the domain. The domain is going to be all x, minus infinity to infinity. Okay? What's the range of inverse tangent of x? Well, it's going to be minus pi over 2. Actually, non-inclusive. In fact, I should have made this non-inclusive. That's my bad. So we get minus pi over 2 to pi over 2. Not inclusive because you never actually reach the horizontal asymptotes. This is the range of inverse tangent of x. Let's go over to my laptop and let's do one more graph on Desmos. Okay, one more graph. We'll erase this stuff here. Let's erase it. Y equals tangent of x. We get that. Now we're going to do y equals arc tangent of x. That's what we get. Too bad those colors are pretty similar. I'll do a line y equals x. And so let's zoom in here. Now we can look here. These colors are similar, but this is tangent of x right there. This is the arctan or inverse tangent of x. This is the line y equals x. They're a reflection about that line. And that's basically inverse tangent of x. Now, if all this stuff blew you guys away, don't worry too much. This is the theory basically, but it's good to know the theory. I want to do a couple quick practice problems with you guys involving inverse trig functions. Very simple. These are the only 3 inverse trig functions we're going to do. Let's do a couple quick practice problems. So these are example problems. Examples. Here's one. Let's suppose we have this equation, sine of theta. We have an equation, sine of theta equals 0.75. Okay? Sine of theta equals 0.75. We want to figure out what the value of theta is whose sine of theta is 0.75. How do we figure out the value of theta that makes sine of theta equal 0.75? We take an inverse sine of both sides. Okay, so if we do that, we get inverse sine of sine of theta. Okay, what is the inverse of the function itself? The inverse sine of sine, these two negate each other. We just get theta. On the other side, we have inverse sine of 0.75. And now you guys can put this in your calculator, take the inverse sine of 0.75, and we get 48.6 degrees. Okay, you also could express this in radians. This comes out to 0.848 radians. Okay, be careful what mode you're in. Whatever mode you're in is the answer it'll spit out. So if you're in degree mode, it'll spit out an angle in degrees. If you're in radian mode, it'll spit out an angle in radians. Very simple problem involving inverse sines. Okay, let's do one more problem. Let's suppose you're building a ramp whose height, you want the height of the ramp to be 2 times the horizontal length. You want to build a ramp whose height is 2 times the horizontal length. Okay? Let's draw a picture of this. That's a pretty steep ramp, right? Here's your ramp. This is your ramp. You want to build a ramp whose height, this is the height, is 2 times the length. So if the horizontal length is x, the height of my ramp is 2x. Okay? The question I have is, what is this angle? What is the angle? Here's the question, what is theta? What is the angle of this ramp? Well, which trig function should we use here? The best trig function to use is tangent. So we'll use tangent. We know that tangent of theta equals the height equals opposite over adjacent. In other words, it equals 2x over x. Okay. Now these x's will cancel, leaving us just with 2. Okay. And then how do we find the angle the tangent of that angle equals 2? We take an inverse tangent of both sides. So inverse tangent of theta simply equals theta. And then we get the inverse tangent of 2 over here. Okay? And if you take the inverse tangent of 2 in degrees, you get an answer of 63.4 degrees. 63.4 degrees, okay? So this is the angle of our ramp. Often we need to use inverse trig functions too in building, not only building a ramp, but like I built a cabin and I had to do similar calculations for the pitch of my roof, for instance. So this is a good, these are some good inverse examples, simple examples of inverse trig functions. Okay, well that concludes this video lecture. I hope this helped you guys understand inverse trig functions a little bit better. Again, I'm going to post this to YouTube. Please watch this video before Thursday, April 2nd's class, and then I'll talk to you guys soon at 1:30 on April 2nd. We can go over some of these things if they didn't make sense. All right, thanks. Bye.